So first of all, I'm extremely grateful to Alan and Johnny and Dimitri for organizing this. And I'm grateful for all the people who've trusted me with so much of their time. And I hope that this will turn out to be a useful and fruitful meeting. Also, I'm just delighted to be back here. As Jill mentioned, I got my undergraduate degree at Brown in 1975, so I'm back here 40 years later. And this place wasn't here. Actually, the building didn't exist back then. And it seems to be a fabulous building. I'm going to try to make use of the space. I thought it's going to be pretty tough to just watch slide after slide after slide for an hour. 2.5 hours a day for 5 days. So I have slides that are going to sort of guide the lecture, but I hope to mostly be following, writing on the board and filling in details. We'll see how that goes. I've never quite used a space like this. As Alan said, it would be great if it was interactive. I'd like feedback, so don't be shy about interrupting, asking a question. And if something's going by too fast, let me know, or if it's bogging down, you can let me know that also. So let's give it a try and see how it goes. So in the nature of this finite element exterior calculus, one reason I think it's a good subject for a CBMS lecture series is that, so it's a relatively new theory. The term was coined in 2006. I think if you start Googling it and so forth, you'll now see that there's quite a lot of people who are working in this area. But there's a certain barrier to access to this area. It involves a variety of tools to get started. So some of the key tools that you need a little bit of homological algebra and a little bit of functional analysis, especially unbounded operators in Hilbert space. And so the homological algebra you need is what's taught probably in many first-year graduate courses and even earlier, but it's the sort of stuff that people who do what we do, numerical analysis, often skip and don't get. So in that sense, it's a barrier. And I want to not assume it, but present some of it. The unbounded operator in Hilbert space theory used to be quite popular, but actually it's not so often taught in functional analysis anymore. So again, I don't want to assume it. And then we get into Hilbert complexes, which are getting close to the main area. This is a sort of obscure area. Actually, I think I remember this right. When Rick Falk, and Ragnar Winter, who are primary collaborators in a lot of finite element exterior calculus, when we started writing down the theory of Hilbert complexes, I don't think we actually knew it was in the literature. But it existed, and with the same name and the same definitions, because it's a natural sort of thing in works of Bruning and Lesch and other people. But we'll introduce that, and when we have these tools, then we'll be able to basically go to the two main subjects, which are sort of an abstract theory of equations related to Hilbert complexes and their discretization. So I'll just abbreviate that by saying approximation of Hilbert complexes. And then key examples will be things like Hodge-Laplacian, which includes things like Maxwell's equations and many other things. And the Hilbert complex will be a version of the de Rham complex. And all this will require another tool, which is exterior calculus, which maybe that's more known in the analytical community, but again, not everybody knows it. So these subjects, I want to go over, and it means that there's going to be a lot of lectures that are initial preparation. And I thought, well, it's a little boring to go for, say, 2 days worth of lectures with preparation when you don't know why you're here. And so I thought I would start out with some motivational examples and try to show some simple computational problems that we can all grasp what the problem is to see why we need to have a fancy theory for dealing with these things. So let me start with the simplest possible example. There might be one trick I didn't know. Maybe can this not be on if... Yeah, that's what I figured. So can I have both layers at the same time or not? So is this going to be working at the same time? No. So how do I put it on and off?
So with that, just have to click.
Okay, now I have this thing, and then where do I click to turn it off? That. Got it. Okay, thank you. No, don't go away. It wasn't as easy as you said. Oh, it has, so this, the little hand, which I hate those little hands, I'll put it down in the corner. Okay, cool. So I'm going to start with some computational examples. So, of course, what we're here about is basically we want to solve boundary value problems and partial differential equations using finite elements, and we'd like to know that these methods converge and study how they converge. So let's start with the simplest possible example. Say minus Laplacian u is equal to f in some domain in Rn, and say u equals 0 on the boundary. The model problem for sort of all finite elements. And let's even start simpler than that. Well, okay, so what's the simplest finite element method? We write this in weak form to find a u in H01 such that the integral of grad u dot grad v is equal to the integral of fv for all v in H01. And then we choose a subspace vh in H01, and we have a numerical method which is to find UH in VH such that this holds for all V in VH. Okay? So that's the standard weak formulation and Galerkin method. And let's really do it in the simplest case. Let's do it where one dimension, so this is just the second derivative of U. So the first example I'll do is just the integral of U prime V prime equals the integral of FV for all V in VH. And U and VH, and I'll do really the simplest case, just piecewise linears, okay? So surely this we understand well. So I take our interval, I divide it up into pieces, and I consider the space of all piecewise linear functions like this for VH. Okay, and of course, this space has a nice local basis consisting of these hat functions that are 1 at one of the mesh points and 0 at all the others. The same thing in 2D. And here I've taken a problem with a simple solution of the cosine. And if you have very good eyes, you can see that there's a blue curve under the green curve. The blue curve is the exact solution U, and the green curve is the piecewise linear, and they're so close you can almost not distinguish them, even with only 14 mesh elements. If you look at the derivative, so the blue curve is U prime minus U prime, and the green curve is minus UH prime, which is a piecewise constant, and you can distinguish the difference, but it's done fairly well for 14 elements. So the finite element method works, which doesn't surprise us. So now the next thing I do is take a problem that's almost as simple. Namely, I go back to where the Laplace equation comes from, and it comes from really two equations. One is that sigma is minus grad u, you define the flux, and that the other one is that the divergence of sigma is equal to f, plus the boundary conditions. And then we can write a weak formulation for this. Let's see, that would be to find a sigma and a u such that the integral of sigma tau, try to get my signs right, minus div tau u, that's right. So let me write it as, yeah, u div tau equals 0 for all tau. This equation we got by multiplying the first equation with a test function tau and integrating this term by parts and using the fact u is 0 on the boundary. So we already have the boundary condition in here. And the integral of div sigma v is equal to the integral of fv for all v. Or in one dimension, it would just be the integral of sigma tau minus the integral of u tau prime is equal to 0 for all tau, and the integral of sigma prime v is equal to integral of fv for all v. And if we look at it, we see that sigma and tau are differentiated, u and v are not. So if we take u to be in L2 and sigma to be in H1, all the integrals make sense with also tau in H1 and v in L2. So that's the weak formulation of the Laplacian, where we've written it in first order form, or we haven't moved it into second order form. And if we do this on the higher dimensions, then it's not H1 anymore, because we don't need all the derivatives of tau, but just the divergence. So it's the space of function sigma in H div, which means that both sigma is an L2 vector field whose divergence is also in L2. Okay, and u is still in L2. Okay, so that's another weak formulation of the Laplacian. You're actually physically even more natural than the first one, although we tend to be more used to the first one. And so now let's do the same thing. So let's go over here and replace these spaces with some SH and VH. And then, of course, we would also put here tau in SH and V in VH, and we'd look for a sigma H and a UH. Okay, what spaces should we use? Well, for example, we could use continuous piecewise linear functions for both sigma and tau. Let's just stick with the 1D case first. Just use the same space that we used here, except no boundary conditions, since they're already built into here. Okay, then we get our first problem. That method doesn't work. Why doesn't it work? Because actually, this finite dimensional problem, which is just a linear problem, so it's, I guess I should have said that, in any of these cases, once you take a finite dimensional space, you choose a basis of it like our local basis, you get a nice matrix problem, right? A square matrix to invert, where the number of equations are the dimensions of SH cross VH, the number of unknowns is SH cross VH, and the number of equations is SH cross VH. So now I take piecewise linears for each, and I write down that matrix, and it's singular. So I can't solve this problem. So if I take SH and VH to be continuous P1 piecewise linears for both things, then I get a singular matrix on the 1D example. And you can see that easily, because take a function UH that looks like this, and take sigma H to be 0, and then you plug those into here. Well, all the terms, these two terms that involve sigma are 0, obviously, and UH is orthogonal to all piecewise constants, so this is 0 too. So you have a non-zero solution of your linear system. So that's total failure. You can't even do the method. So already there's something to think about. So then let me take two other choices. Continuous P1 for SH, but piecewise constants. So I'll just call that P0 for VH. So here we use the space of piecewise constants. And then the other possibility, let's improve the accuracy by going up to continuous P2, piecewise quadratics, for SH, and P0 again for UH. Okay, well, let's, on the next slide shows what I have here. So now there are three curves on each of the two pictures. Again, we have u on the right and sigma on the left. The exact solution is shown in blue again. Now, so I am not showing the linear method because there's no solution to show. For the linear constant method, we get the green curve. So u is a piecewise constant, and that's why we have this green piecewise constant. And it's doing about as well as a piecewise constant could do. So this is working well, for u at least. And if we look at the green curve for sigma, well, sigma's the piecewise linear now, and it's hiding the blue curve, so it's doing perfectly well. So this works. And then the second method is the red method. And in that one, u is a piecewise constant again, but it does not do a good, decent job of approximating the solution. And the red is a piecewise quadratic, and it's totally crazy, highly oscillatory, has nothing to do with the exact solution. So this fails. It's not singular, but the computed solution is all wrong. Okay, so even in this unbelievably simple example of solving u double prime equals f, or u prime sigma equals u prime sigma prime equals f in one dimension, it's a little bit funny. It's not, things don't happen in a completely straightforward way. If you hadn't seen things like this before, it would be a little bit surprising. Any questions about this first computational example? Okay, why is this going on? Well, those of you who study numerical analysis, whenever you study any numerical method, the first thing that should pop into your mind is that convergence is essentially equivalent to, in particular, it follows from consistency and convergence. I thought of giving a lecture, a part of a lecture just on consistency. Oh, no, yeah, convergence follows from convergence. Okay, you're all awake, very good. The most important word. You need consistency and stability imply convergence. It's basically the fundamental theorem of numerical PDE, or fundamental theorem of numerical analysis. It's actually sort of a meta-theorem in the sense that it seems to be treated differently in every different context. I just wrote an article for a forthcoming encyclopedia Springer has on applied and computational math on that subject. So I have a 13-page article on this. And there really is one theorem that covers all the cases in some sense. And I thought of lecturing about it, but I think the audience knows this. But let me just remind you, in this context, what are consistency and convergence? Well, for finite elements, for Galerkin methods, consistency is measured by having a small consistency error. And that would be if you take your bilinear form. So here our bilinear form, B of uv is this. And here our bilinear form, B of sigma u tau v is this. Consistency error is you take B, you put in a known good approximation of u, like the interpolant or the best approximation or something like that, in the subspace. And you compare that to if you you put in the best approximation of u, and then our original problem was B of uv equals fv for all v in, and our numerical method is B of uh equals fv for all v in vh. So now you put in the best approximation of v in the subspace, and you look at this difference. And then you do that for v in vh. and you take the supremum of that over all v and vh, non-zero, and you normalize it by the norm of v, h. That's the consistency error in finite elements. So if we put the exact solution in here, we get 0. And so this is somehow telling us whether the best approximation is close to the exact solution. So if we know the best approximation is close to the exact solution, the consistency error is small, as long as the exact solution really satisfies this equation. Sometimes we have methods, non-conforming methods, methods with numerical integration, where there's some more consistency error because the thing that we compute with, this is the one we actually compute with, which might be changed from the real one. Okay, so that's how you measure consistency error. It combines two things: how well the space VH approximates the true space that you're dealing with, where the solution lies, and if you how much you messed up the bilinear form when you computed. In our examples, we didn't mess up the bilinear form at all. We did exactly the same form. So these are just approximation errors. And so all the examples I put in have small consistency error. Well, so we need to put some norms on these spaces. These are all Hilbert spaces, so the true solution U has some nearest function in the Hilbert space. But for this, you can use either the best approximation or some known good approximation, like the interpolant or the L2 projection or something. Okay? I don't want to get too deeply into this, but I just want to emphasize that consistency means, in these contexts, that your finite element space has good approximation properties. The solution can be well approximated. But that's not enough. That's the main thing I want to say. Consistency does not imply convergence. If it did, all these examples would work. You need also stability. And what's stability? Stability is the mapping from the data to the discrete solution, the mapping from F to UH. We need, first of all, the mapping from UH to F is invertible, so that you can go back from data and compute UH. And then we need that the norm of that inverse is bounded uniformly in H. So this has to do with a bound on the discrete operator inverse. So LH is what's taking us from VH to the data, the discrete data. So it's basically the matrix that you get should be invertible with an inverse that's not too big. So this method is completely unstable because it's singular. And this method must be, since it failed, must have a very large inverse to that matrix. And that's what goes wrong. Okay, so that's the setup on a very, very simple example. Okay, and so the whole game in much of numerical PD is how do we get numerical methods which are not only consistent, which is easy to do, but also stable. And as I'm just trying to point out, that even with such a simple bilinear form, it's not obvious. Okay, now let's go to 2D. So same problem here, now it's here. Sigma and H div, U and L2, and we want to satisfy this system of two equations for all tau and H div and V and L2. And of course we'll take subspaces SH and VH. Okay, well, based on this, we probably don't want to spend a lot of time thinking about continuous P1 for both things. In fact, it's singular again. We might say, well, here's a nice, easy solution. Continuous piecewise linears for sigma, piecewise constants for U. In 2D, that fails. So that's what's plotted here. In this case, this is the choice continuous P1 for sigma and piecewise constants for U, and I'm only plotting the U variable. It's not as easy to plot a gradient in 2D, and so I didn't bother. And what you see is wild oscillations again, but now you're getting it with the P1, P0 element. So you see the solution U, which should be, you know, there should be some nice two-dimensional analog of that, just some nice bubble on the square, instead is wildly oscillatory in the numerical solution. It goes negative, which it shouldn't be. The solution should be positive. It's all wrong. So in 2D, if we have SH is continuous P1 and VH is P0, then this is clearly from the computations unstable. Not singular, but very bad. On the other hand, in 1976, a set of finite elements were invented that solves this problem well by Ravi Artoma. In what was really a seminal paper in 20th century numerical analysis. It's taken many years for people to appreciate the importance and depth in this, and this is a paper that gets cited 80, 100 times a year now, 30 years later. It was written the year after I graduated from Brown, so it's very old. And what did they do? They said for SH, they created a new space, and what their space is its piecewise polynomial vector fields. On each triangle, the polynomials have the particular form A plus B times X, C plus the same B times Y. So SH is the set of, restricted to T, is the set of all functions of that form where A, B, and C are real numbers. So it's a piecewise linear vector field, but not an arbitrary piecewise linear. There are a 6-dimensional space of piecewise linear vector fields, but these are only a 3-dimensional subspace. And then you also have to say how they'll be attached from one triangle to another. And they'll be attached by asking that if sigma h is in SH, that should mean that the normal component of sigma on the edge of a triangle should be continuous. The jump should be 0 across element edges. Okay, and that's a nice finite element space to work with because you make any triangulation and you just say what you want the normal component to look like in the middle of each triangle edge, give it a value, and there'll be a unique element of this space with those values. That's the Ravi-Artoma space, the lowest order case of the Ravi-Artoma space. And then they took that SH, and they took continuous piecewise constants for U, and they proved that that was stable. And that's the picture on the right here. So here U is again a piecewise constant, so it can only do so well in approximating a smooth function, but you see it has the right shape and character, and the error is not too small. And if you refine that mesh, it'll converge nicely. Okay, so there's a big difference between a stable method and unstable method, a huge difference, and it's not some subtle little point that it's the difference between night and day. Okay. Now, the next problem, so any questions? Yeah.
Is it the lowest order of the Ravi-Artoma?
That's the lowest order Ravi-Artoma space. The vector fields on each triangle consist of constants and certain linears. The next order would be linears and certain quadratics. And they would be paired with piecewise linears for U. Okay, and we'll see the full set of spaces for the Ravi-Artoma in n dimensions as we go along the course. Constantine?
The ideal Ravi-Artoma was pure luck, or it came out from above from some kind of pure?
No, it surely was not pure luck. It's an example of a problem. So as I was just getting started in this business, actually, then I was not in this business. About 4 years later, I was getting started. So I was at University of Chicago for my grad work. I started working in numerical analysis towards the end of that time in 1977, 78. We had a seminar where we read the Ravi-Artoma paper. By the way, there's all this talk about what journals you publish your paper in, you put it in a good journal. That was in a conference proceedings in a Springer lecture notes. So we read this paper, and actually I got a summer job implementing it. I think I'm the first person to ever implement the Ravi-Artoma method, and I did it all on punch cards. I had a big thick set of punch cards like this. Actually, I'll tell this whole story. So that summer job, my advisor, Jim Douglas, had a lot of connections with the petroleum industry, and he got funding. He believed, correctly I would say, that these methods would be very appropriate for modeling subsurface flow in oil reservoirs, Darcy flow equations, because there's a good reasons to be using the first order form for those. And he got funding from Shell, Mobil, and Exxon to support a graduate student to experiment with Ravi-Artoma. That was me. And we gave that work. Then, about 2 months ago, I was on an external review committee to review strategic corporate research for ExxonMobil. They have a strategic corporate research lab with about 170 PhDs in Annandale, New Jersey, and I spent several days listening to them give presentations what they did. They had just discovered the Ravi-Artoma methods and how important it was, and were doing all sorts of experiments with it. And they're quite excited about it now. And I pointed out that we had submitted a report 40 years ago saying that this was the appropriate thing to do. It shows it's, and they said maybe we should set up a consulting arrangement. So that shows you how serious they are about this. But it shows how long it takes to get these ideas. So now to get to your question, how did they come to this and why? So in those early days of finite elements, many of the good ideas came out of the engineering community, where you might say finite elements was invented by Courant or somebody like that in a theoretical context, but it didn't become real till the 60s when the engineers in the aerospace industry started to use it. And they invented all sorts of good ideas and things, but they did things by mainly intuition and testing. And my belief is consistency is entirely intuitive. Everybody understands a method has to be consistent. Can't be any good if the finite elements don't have good approximation. But stability is not intuitive. And the engineers didn't arrive at this so much. And who did? Well, a lot of people did. Babushka did. Bretzi did. Various other people, Fix and Strang and Nicolaides had ideas on this and so forth. In particular, Bretzi considered saddle point problems, of which this is an example, and said, well, you want stability, this is what it has to be. And he did it by using functional analysis and so forth, and he came up with the famous Bretzi theorem and the Bretzi conditions. And Ravi-Artoma looked at those things and said, well, actually, so the goal, the golden grail, was to solve the elasticity equations in mixed form. So not the Poisson equation, but the elasticity equations was what people want to solve, where you had the stress and the displacement. And nobody, so engineers were trying it all the time. They were publishing papers or not publishing because the results didn't work, where they tried this element and that element, nothing ever worked. And then Ravi-Artoma did something that mathematicians tend to do and said, well, we can't solve elasticity, let's solve a problem that nobody's interested in, the Laplacian in first order form. They thought nobody was interested because everybody could solve the Laplacian in second order form. They weren't right. Actually, people are very interested in it. But so they dropped down to this easier problem, and it still wasn't easy, but using the Bretzi conditions, they came up with some spaces that would work. And actually, if you look at the first version of the paper, the spaces weren't what we call Ravi-Artoma today. The lowest order was, the higher order ones weren't quite right. There were things to be changed and so forth. But they knew what they were looking for. They understood Bretzi's theorem, and that's what led them to getting these elements. And then I was part of the world that was trying to transfer this from the math world to the engineering world, and I guess it took us a long time. I was at conferences, in engineering conferences, where people stood up and said, oh, these mathematicians. There was even one conference I didn't realize in the audience, and they used me by name, said they're trying to convince us these Ravi-Artoma elements are important, but we tried them, they don't really work, or something like that. That's all completely changed. They're embraced in the computational engineering world and now making it into the industrial levels. Any other questions? When was what? I think the paper is 73, is it, Rick? Something like that, 73 or something like that. In a paper that's very difficult to read and was really difficult to read at the time, but by now has been cleaned up and is so elegant and nice.
What is the main reason for coming back as a petroleum? Conservation?
There's a few reasons. That's one is conservation. The other one is the rough coefficients and the fact that sigma is a lot better function than grad U in applications. The other...
It's not always true, right?
It's not always true, but it's widely true and experimentally makes a big difference. Then another is that the stress-strain law, which is the flow-flux law, the velocity-flux law, in some cases is not invertible. So I'm not sure how much I'm allowed to talk about what ExxonMobil's doing, but when people are looking below the subsurface now, they don't always use their seismic waves, they don't always use elasticity, they're interested in viscoelasticity and more complicated laws, and some of them can only be written in a system. You have to remember the physics of the problem is you have two very different rules, a constitutive law, first order rule, and a conservation law. And it's only us who say, oh, wouldn't it be easy to put them together and have one second order equation? But that's not the physics, and it's not always possible.
I mean, always trying to say to people that mixed method is total natural, will find that volume method on the other is totally unnatural.
Okay, well, we'll mark that for the record, but I'm not going to go there.
This might be a little bit off topic, but I know that some people use some of these methods in discretization that don't work, but then they put in stabilization terms, correct?
Yeah, I don't know how much philosophical I should get. So my view on these questions is we have huge number of numerical challenges to solve, right? We can simulate the bending under small deformation of an elastic plate. We can simulate the flow in certain non-turbulent regimes and so forth. But in real life, we'd like to be able to simulate the world, which is much more complicated. And there's lots and lots of stuff we need, difficult, challenging problems to do. Whenever a naive person who doesn't know numerical analysis comes and say, I have a numerical problem for you, it's very easy, I think you won't have any trouble, they always give me something that's totally impossible to do with current technology. So what do? Well, you do the best you can with the tools you have and the understanding you have. A lot of times you don't have the perfect method. You live in the region, in the era before Ravi Artoma discovered those elements, you don't know what to do. So you do the best with the tools you have. Stabilization of various forms, bubble functions is a trick, different kinds of tuning of penalty, many, many different things you can do. And a skilled numerical analysis and a skilled scientific computer can get very far with such tools. In other cases, you have exactly the right tools for the job. And the finite element exterior calculus is for a certain class of problems trying to find exactly the right tools for the job where these tricks aren't necessary. Okay, so let's see. The next problem I want to talk about is closer to the ones that, well, this, so by the way, this behavior we'll see, this will be explained more fully in the framework of the finite element exterior calculus, although we certainly don't need that framework for it. It's understood just with Bretzi's theorem and older tools. You know, on the screen there's a button you can click and it erases. Maybe you need to get one of those. Okay, the next example is just a tiny bit more complicated. And let's get it on the screen. So the equation is, I'll write the equations in 3D, but I'll illustrate them only in 2D. Curl u minus gradient of divergence of u is equal to f. So we're given f from omega to Rn, and we want to find u, a vector field u, such that these PDEs hold with boundary conditions, and I took so-called magnetic boundary conditions, u dot n equals 0, and the tangential component, curl u cross n, equals 0 on the boundary. This is one scalar boundary condition, and since this is a tangential vector field on the boundary, this is two conditions on the boundary. So altogether in 3 dimensions is 3 conditions for a 3 vector field. Okay, those of you who remember your vector calculus remember that this could be written as Laplacian U1, Laplacian U2, Laplacian U3. The Laplacian applied to each component of the vector. That's not a particularly useful identity for most of this work. We'll stick closer to where it comes from. Particularly, the Maxwell's equations is very related to this in the case F is divergence-free. Okay, so there's the problem and the wrinkle that I'm throwing in this example. So to solve it, I multiply the equation by a vector field V and integrate the curl by parts and use the boundary condition, and integrate the gradient by parts and use the boundary condition. And so we find for all u satisfying the boundary we find that u satisfies this equation for all, and that's a typo, v, which satisfies the boundary equations. That should be integral of fv. And I told myself I'm going to keep a list of the typos if it doesn't get too heavy. Okay, and the wrinkle I'm going to put in, I'm going to solve it on a domain which has a non-convex corner, Jill Pfeiffer's original area of specialty. So what I'm showing you here is I put down a mesh, a fairly moderately fine mesh of triangles on this L-shaped domain. And I did this computation, and I used u to be continuous piecewise linears and v to be continuous piecewise linears. Now you might think that we don't have stability problems now because we have a positive definite bilinear form here. However, what we find is that as we refine the mesh, UH converges to some function, and it's this function here. That's actually a numerical solution on a moderately fine mesh. And that's nothing like the exact solution. The exact solution, or an approximation of it with a better method, is shown here. Okay, so this is the solution to the problem. Because of the reentrant corner, it has a sort of pretty strong singularity at the reentrant corner. This is what happens if you compute it using standard piecewise linear finite elements. They're remarkably different. If you refine the mesh, it doesn't get any better. It converges to the wrong answer. So we might ask ourselves what's going on. We know that the method would work if it's consistent and stable. Well, actually, this problem is actually a problem of consistency, not stability. Because of that positive definite bilinear form, this method is stable. But the problem is, if you take u is the solution to that problem, and you ask how good is the best approximation of u for all v in the space of continuous piecewise linears, this doesn't go to 0. As the mesh is refined, because of the strength of this singularity, where here we put, for example, well, what norm am I putting here? I'm putting the norm that comes from the bilinear form. So the norm would be the norm of the curl of u squared and the divergence of u squared. And you can choose to put in u squared itself here. It's probably a good idea. If I put a 2 here, this would be exactly the h curl norm plus the h div norm squared. If we use this norm, the natural norm of the problem, the energy for the problem, then the method is certainly stable because it's just minimizing the energy. But in this norm, you cannot approximate an arbitrary, a function that has that bad singularity with piecewise linears. So this is a failure of the standard finite element method for what seemed like a very simple problem. You might have thought since we can do the scalar Laplacian, we do the vector Laplacian in the same way. And if you thought that, you would be wrong. The same problem happens not only with piecewise linears, but essentially any conforming finite elements that you use in this formulation. Any continuous piecewise polynomial space has the same problem. So we need different finite elements. What's the problem here? The problem is this space, h curl intersect h div plus boundary conditions. This is not an easy space to deal with finite elements, unlike the Sobolev space H1. On a smooth domain, this is equal to H1 plus boundary conditions. But on a domain with a reentrant corner, it's not. How do we solve this then? What's the solution? Well, later in the course, I'll give you a MITS method where we introduce a new variable. For example, we could introduce sigma's curl u as a new variable, write this as a system, and use appropriate mixed finite elements a la Raviart-Thoma, and we get a good method. And that's actually how this was computed. But the problem is not only the fact that we have a non-smooth domain. Here's an example of a problem with a smooth domain. Same equation. The domain is an annulus, or if we do it 3D, turn it into a 2D problem by making an annulus and take everything independent of z, basically. So we have the same equations, same magnetic boundary conditions, and here we have a problem at the PDE level. This boundary value problem does not have a unique solution if the domain is not simply connected. It's not true that if f is 0 and the boundary conditions are 0, and curl, then u has to be 0. And that's easy to see. Take your annulus, use polar coordinates, r and theta, and take u to be the gradient of theta. Well, then we have the curl of u is equal to 0, because the curl of a gradient is 0. And the divergence of u is equal to the Laplacian of theta, and theta is the imaginary part of a harmonic function. It's harmonic. It's imaginary part of an analytic function, so it's harmonic. So obviously that bilinear form is that we're going to get when we integrate by parts. Well, obviously curl u minus grad div u is 0, because curl u and div u is 0. Also, you easily check the boundary conditions. In fact, there's a picture of gradient theta in the green annulus, and you can see that its normal component is 0 on the boundary, and its curl is 0 everywhere, so we get a non-zero solution. So the existence of a hole creates this problem, and it tells us we were solving the wrong problem to start with. We can't solve that numerically because it doesn't have a solution. The problem we should have been solving was we introduced the kernel of the operator, which in this case is just the span of this one function. So it's a theorem from geometry that we'll be getting to, that the dimension of the kernel of this boundary value problem is the number of holes in the domain. So in this case, 1. And the problem we should have been solving is curl u minus grad div u is f modulo that kernel, because we can't do anything else. If f is not orthogonal to that kernel, there is no solution. And what's more, we would not have a unique solution unless we insist that u be orthogonal to that kernel. So this problem is well posed with that one-dimensional kernel. Now, so let's take this nice well-posed problem, which is sort of a fundamental problem in mathematical physics, rises, say, in Maxwell. And let's solve it by putting some nice mesh of triangles on our annulus and using continuous piecewise linears for u. Then you get this picture here. You get something that is just actually, this is quite a large multiple, I didn't give the scale, a large multiple of that function, which is not what we want. We want a solution that's orthogonal to that function. So this is wrong. The true solution looks like this, and again you see they look nothing like each other. It has a very different topology of solutions, completely different. The numerical method completely misses it if you use continuous piecewise linears. Why? Because when you try to compute this on the numerical level, you compute the kernel on the numerical level, you'll find the matrix is non-singular. It's non-singular, there is no kernel. So the numerical solution doesn't mod out anything, doesn't imply the side condition, it loses this condition entirely. How could it possibly be correct? So you see the well-posed problem that we had has a side condition. You have to be orthogonal to harmonic forms. The numerical method didn't capture that. It can't possibly be right. You can't throw away one of your conditions and still hope to get a good answer. Okay, so that's another example to motivate this. Any questions? So the final example I want to talk about is the Maxwell eigenvalue problem. So that's related to this problem we've been talking about. The fundamental eigenvalue problem for electromagnetics is curl u is equal to lambda u, and div u is equal to 0. And some boundary conditions like the type we've been talking about. So a weak formulation of that you get by multiplying the equation by a function v and integrating by parts, and that'll get you this question here. So we're trying to find a real number lambda and a non-zero u and h curl such that curl u curl v rates to the lambda integral uv for any v and h curl. I've thrown away this equation, and obviously I can't do that. What happens if I do that? Well, the thing is, if you have any solution of this, it automatically satisfies div u equals 0 because you take divergence of this equation, you get 0 equals lambda div u. So if lambda is not 0, if you have a non-zero eigenvalue, div u equals 0 is implied. On the other hand, if I throw away this condition, I will get all sorts of 0 eigenvalues, which are just any gradient. So u equals gradient of anything satisfies curl curl u equals 0. So one way to try to solve this problem is find the non-zero eigenvalues of this problem. So now let's look at it. So here's our problem. I take a mesh of the square. In this case, I took a non-uniform mesh of the square. I did the square because we know the exact eigenvalues by separation of variables. They are, well, there's the 0 eigenvalue with infinite dimensional space of eigenfunctions, the gradients. And then anything in the form m squared plus n squared. So 1 is a double eigenvalue, 2 is a single eigenvalue, 4 is a double eigenvalue, 5, 5, 8, etc. So we take this, we take continuous piecewise linears. I'm really coming down heavy on those continuous piecewise linears. And this is the spectrum that you compute for the discrete operator. It's those dots. And they should fall on 0, and 2 of them on 1, and 1 of them on 2, and 4, 4, 5, 8, 5, 5, 8, and so forth. And you see there's no relationship visible between the spectrum of the discrete operator and the continuous spectrum. So it fails totally. The numerical spectrum looks nothing like the continuous spectrum. Raviartomas come to the rescue again. For H-curl problems, you need the so-called rotated Raviartomas, where instead of normal derivatives, you have tangential derivatives. So all you do is you take the space and you rotate it by 90 degrees. So instead of a plus bx, c plus by, you rotate it 90 degrees. So you get minus a, which we'll call, say, minus c, which we'll call, say, alpha, minus by, gamma plus bx. So a three-dimensional space now, but now it's minus yx instead of xy because of the rotation. So you do those guys, and you compute the eigenvalues of the matrix you get from here. And what you find is 145 eigenvalues that are precisely 0, and then 2 eigenvalues that are very close to 1, and 1 to 2, and 4, 4, 5, 5. And so you capture the spectrum almost exactly, where the big eigenvalue at 0 is a large kernel to your matrix. And the positive eigenvalues capture what you wanted exactly. A very interesting example came up from Daniele Boffe, Franco Brezzi, Lucia Gastaldi, who did the same problem and analyzed it on a crisscross mesh, a uniform crisscross mesh. And of course, the Raviartoma method works fine. But here's what you get if you use continuous piecewise linears. You get this picture. Nothing like the bad one we had before. And it looks pretty good. 1, 1, 2, 4, 4, 5, 5, 6, 8. Then you say 6. It's not supposed to be a 6. That's spurious. So you go to your numbers. Here's a mesh of 254 elements, 570 elements, 1,000, 1,600, and so forth. And there, say, here's 2, 0.01, 2.00, 2.004, 2.002. This is clearly converging to 2. But this one seems to be very clearly converging to 6. It's completely wrong. So that's another sign of what can go wrong with an unstable method. We will prove that for a stable method, all the eigenvalues converge and there are no spurious eigenvalues. Unstable method, can fail spectacularly or can fail subtly. Subtly is much more dangerous. Subtly is the ones that you believe and you build the bridge and it collapses. And the final slide is I just wanted, these are all very academic examples, and that's what I want because I want to show these are fundamental issues we have to figure out how to address and understand. But of course, the real interest is real problems that people want to solve, and the kind of techniques we've talking about are used in very serious computations, especially electromagnetics. These are pictures from Schoberl's group of, for example, this bus bar, which comes from, I think it's Siemens, or I'm not sure, an industrial application, and used tens of thousands and hundreds of thousands of elements in order to do these computations, and of course you have to use a stable, good method. Okay, that's my motivation. Any questions? Yeah. So this will become very clear when I get further into the course. But Ravier-Thoma did HDiv elements, that's normal components, in L2. Nedelec said, we could do these in 3D, not in L2, in R2, two dimensions. We could do them in 3D, but then there's two ways you could generalize HDiv. He was an electromagnetic guy, is an electromagnetic guy, so he knew that you needed H-curl and you needed HDiv. And H-curl in 2D is the same as HDiv rotated, but in 3D it's something totally different. He did both of those. Those are both Nedelec elements. Nobody gets credit for doing rotated Ravier-Thoma because you rotate somebody else's result by 90 degrees, you don't get any credit for it. So I wouldn't call those Nedelec elements.
So if you try high order finite element C1, I would have the same problem?
C1. I don't believe C1 will help you for an H-curl problem. No, I think you would certainly have the same problems. I could be wrong, I haven't done it. But I don't think C1 is the solution to these issues. The problem with these problems is H-curl intersect HDiv is a weaker space than H1. Not a smoother space. It's not closer to H2, it's further from H2. Any other questions? Okay, so now with that motivation, I want to go through Homology 101, and maybe I won't even finish it in this time. So now, this is mainly a lot of definitions. There's no depth to what I say, but as we all know in mathematics, once you start piling on the definitions, it can get confusing. So first we'll start with the chain complex. So a chain complex is nothing other than a sequence of vector spaces and a sequence of maps mapping one to the next. And we index these so the numbers are going down, and in all our examples, when you hit 0, beyond 0, the vector spaces will be 0. And for k large, they'll be 0, so we really only have a finite sequence of vector spaces. There's a bunch of zeros, and then we have some vn and vn minus 1 down to some v0, and then the next one is 0, and then these are all zeros, and these are all zeros. Okay, and when you have that, so you have these vector spaces, and you have these maps, dn from vn to vn minus 1, that's called a chain complex. If one condition is satisfied, these are linear maps, bounded linear maps on a vector, or linear maps, there's no topology at this point, linear maps on a vector space. And the one property you should have is if you do two of these operators in a row, so you do dn minus, partial n minus 1, dn minus 1 composed with dn, it gives you 0. That's the chain complex. So the range of one of these spaces, so let's start introducing the terminology. Bn is the range of, by the way, chain complexes, I made a mistake already. Chain complexes, by convention, always have subscripts, not superscripts. So, which is what I did up there, I hope. So this should have been n and n minus 1, and 0, and n minus 1, and n. Bn is the range of the previous Vn plus 1 in Vn. So Bn is the range space inside Vn. And Zn is the null space of Dn in Vn. And so this condition is the condition that Bn is contained in Zn. So that's our only condition. There's another way to think about it, which is quite useful. Instead of thinking about it as a sequence of vector spaces, you could add them all up, just take the direct product. And so you could define one big space V is the sum over all k of Vk. And then we have a map D that maps Vk to Vk minus 1, so we put them all together and we get a map from V to V, which has the property that D of Vk is contained in Vk minus 1. That structure has a name, but it's the exact same content as this. This is called a graded vector space, and this is a graded linear map of degree minus 1. Minus 1 because it knocks k down to k minus 1. So that's another definition of a complex, is a graded vector space with a graded linear map of degree minus 1 whose square is equal to 0. Same thing in different words. Okay, for reasons that'll become clear shortly, the space of V is called the space of k chains. Zk is called the k cycles, the null space. Bk, the range, is called the k boundaries. And since the boundaries are contained in the cycles, we can form their quotient space and get the quotient vector space, which is the kth homology space. So that's what homology is. And so the elements of the homology space are the cycles, but only equivalence classes of cycles where two are equivalent if their difference is a boundary. So like I say, it's a lot of definitions. Now let's take the simplest example, and the one that explains why you have those funny terminologies, cycles and boundaries and chains. Let me define a k-simplex. Well, we know what a k-simplex is. It's the convex hull of k plus 1 points. Let's assume they're in general position in Rn. And I mean a little bit more because I'm going to remember the order of these points, so we have an orientation. But for now, just think of a simplex. And then the faces of the simplex are themselves simplices. You take any subset of these points, I0 through ID. If you take d plus 1 of them, you get a d-dimensional face. And then a simplicial complex is a finite set of simplices with the two properties that if a simplex is in there, every face is in there. And if two simplexes intersect, then the intersection is a face of each of them. So a simplicial complex in 2D might be these three triangles plus these edges plus these vertices. Those things all together form a simplicial complex. It's very close to what we call a triangulation in finite elements, except we usually only think of the top degree, the triangles, as being the elements. The simplicial complex also includes the faces. And as I say, I'm going to have an orientation on these guys. So by orienting a point, so let's assume that the points in all the points in our simplex are numbered from 0 up to something in some order. So then when I orient it, a point all the points have a plus sign. They're oriented as positive 1. The edges are oriented if they're traversed from lower to higher vertex. And similarly, we have an orientation for a triangle. If you traverse it in order from increasing order, that's called a positive orientation. If you switch any two of these, it becomes a negative orientation. And so all the permutations with positive sign would give you positively oriented simplex, the same simplex back again. But if you switch to a negative permutation, then you would get the negative of this, the negatively oriented. There's an oriented simplex in 3D. Okay, now we define the boundary operator on chains. So here's the notation. Delta k of a simplicial complex is all the simplices of dimension k. Okay, so for k is 0, it's just a set of vertices. K is 1, it's a set of edges, and so forth. Then a k-dimensional chain is just a formal linear combination, finite, a sum of each of the k-dimensional simplices with a coefficient. So it's a vector space in which you've taken as a basis the simplices, and you've made a vector space by taking formal linear combinations. Then we can define the boundary, and the boundary of a k-dimensional simplex is a k-1 dimensional chain. And here's the formula. The boundary of the simplex spanned by x0 through xk is the sum of the simplexes in its, where you leave out one of the guys. So you get a simplex on the boundary, and you put on signs in this way. So they're oriented simplices, and the picture is, if I have this triangle, 0, 1, 2, and so they're oriented in this order, increasing order. Then when I take the boundary of it, I leave out 0, so I get 1 to 2. Then I leave out 1, so I get 0 to 2, but with a minus sign, so that means I go in the opposite order for that edge. And then I leave out 2, I get 0 to 1 with a plus sign. So I get here, if I take this simplex, I get that guy. This oriented simplex, I get that guy. Okay, and of course that extends by linearity to chains. So I have a mapping, the boundary operator that takes a k-dimensional chain to a k-1 dimensional chain. Okay, and so for example, if I have a body that's triangulated with 3 triangles with consistent orientations all counterclockwise, then when I form its boundary, I get this chain, which is just a chain around the boundary in clockwise orientation. So we get a complex because we have a vector space. Our vector space VK is just CK, the k-dimensional chains. Our boundary operators just take the boundary of a chain to get a chain of 1 dimension lower. The boundaries BK are exactly boundaries. The cycles are chains who have no boundary, chains whose boundary are 0. And it's obvious that if you take the boundary of a boundary, you can either do it algebraically or geometrically, boundary of a boundary is 0. So we have a complex called the simplicial chain complex. There it is. N chains, the boundary is n-1 chains. That forms a nice complex. Okay, and algebraic topologists love this because the dimension of this space is one of the most important invariants of the domain that the simplicial complex triangulates. So you look at the homology group. That's the chains at dimension k, which are cycles. They have no boundary, but are not themselves equivalent to 0. So they are not boundaries themselves of something. The dimension of that space is called the kth Betti number. And so here's an example of a cycle, the blue cycle, but it's not the boundary of anything. Why not? Because you try to fill it in, and all of a sudden there's a hole that gets in your way. So the fact that we have a hole is registered by the fact that we have a cycle which is not a boundary. The green one registers the same information, but the green is equivalent to the blue because their difference is the boundary of this little annular region between the two. So you can see how this works. So that's how you define the Betti numbers, and it's the easiest kind of algebraic topology. And so what does this mean? These are finite dimensional vector spaces and linear operators. So you take some matrices and you look at their null spaces and ranges and do some combinatorics, and you can compute the Betti number of a domain. If you do this in n dimensions, well, the nth Betti number let me see here. The nth Betti number, just take the whole, so let's take the 0th Betti number. That's the set of points, and since it's at the end, the next thing is 0, every point is a cycle. So everything is a cycle, and so the 0th Betti number is how many non-equivalent cycles you have. So you take all your points and say how many of these do not generate the same homology group. That means their difference is not a chain. There's no one-dimensional chain connecting them. So the homology group H0 is exactly the number of points which cannot be connected by segments. That's the number of, if your domain is connected, there's only one. All points are equivalent in a connected domain. If we have, our domain is connected, then any point can be connected to any other. So for a connected domain, the dimension of the zero homology group, which is Betty 0, is equal to 1. If you have a non-connected domain, it would be the number of connected components. So the first Betty, the 0th Betty number is the number of connected components, and it has some topological information. The first Betty number, that's the number of cycles of one dimension that are not boundaries. That we saw as the number of holes. So for a donut's connected, so the first Betty, the 0th Betty number is 1, and it has one hole, so the first Betty number is also 1. The second Betty number measures holes in a three-dimensional sense, places you could store water, voids in it. So if you had a ball is hollow in the inside, so it has a hole in the three-dimensional sense, even though it's simply connected. So the number of such voids is the next Betty number. So donuts are not hollow, or at least this donut is not hollow, so it has the next Betty number 0. Coffee cup is topologically the same as a donut, so it's the same. But an inner tube, that's hollow, so we have a Betty number of 1 in the second position, and it has two different kinds of holes. There's, two different kinds of cycles that are not boundaries. There's ones that go around this way and ones that go around this way. So this first Betty number is 2, and so forth. The difference between the donut and the inner tube? Right. Inner tube is hollow. You could, so that's a hollow torus, and a donut is solid torus. Okay? So there is a void in here. If you fill in that void, then you lose this 1, and you get a 0 here. Okay, so that's the complex, the grandfather of all complexes that gave birth to the definitions. And let me see. Okay, so I'm actually not going to finish because I don't want to run over. Even 75 minutes is not enough. So I'll give you one more definition and then we'll stop. There's a natural map between complexes. So here's a chain complex with spaces V and boundary operators D. And here's another one with spaces V prime and boundary operators D prime. A map between these, that would be a map that takes each VK to VK prime, call it FK, and which commutes in this diagram. So D prime of F is the same as F of D prime. That's called a chain map. And why are chain maps important? Well, because chain maps take cycles to cycles. So let's see that. If I have so I have VK, VK minus 1, V prime K minus 1. I have something in here that's a cycle. So that means I have a Z, and D of Z is 0. What happens if I look at F of Z? Well, D of F of Z is F of D of Z, and D of Z is 0, so that's 0. So cycles go to, so F induces a map from cycles to cycles. I'm not writing Z in the same way. In a similar way, F maps boundaries to boundaries. Because if I do F of D of something, that's D of F of something, and so it's a D. So it takes cycles to cycles. And therefore, I get an induced map, F bar, which takes the homology of the first sequence to the homology of the second sequence. Just by F bar of the equivalence class of some Z cycle is you take F of Z, that's also a cycle, and you take its equivalence class. And that's well defined because of this. And that creates a map with good functorial properties if I have a complex V and a complex V prime and a complex V double prime, and I have chain maps F and G here, then G composed with F, it creates an induced map, which is exactly equal to the induced map of G composed with the induced map of F from homology of the first sequence to the second sequence to the third sequence, F and G. And one particular case is if we have a subcomplex. That would be the case where we have one complex, let's call it W, which is contained in another complex V. So in that case, we have inclusion maps going down, and inclusions obviously commute, so that's a chain map. The inclusion of a subcomplex is a chain map. A subcomplex means that not only are the WKs subspaces of the VKs, but the D of WK maps into WK minus 1. That's our property to define a subcomplex. And I'll stop with one small theorem, and which is very simple, which is, suppose we have a complex and a subcomplex. So we have our complex V, and we have our subcomplex W, and suppose that there exists a chain map down to it that's a projection. So that means Fk of W is equal to W if W is in WK. So F is a chain map, but also a projection. So it's a chain projection. Well, I could also write WK up here and put the inclusion map here. And of course, projection occlusion followed by projection is equal to the identity. So therefore, the induced map, induced by inclusion, induced by projection, is equal to the induced map of the identity, which is the identity on homology. And that shows that this map must be a surjection, because it follows something and gives you the identity. It must be a surjection. So if you have a chain projection, it induces a surjection, at least on homology, and we'll use that. Okay, so I better stop, and I'll continue this in the afternoon. We're almost done with the homology part of it. But I want to go over the next important example of a complex, which is very different, which is the de Rham complex. So I'll do that in the afternoon. Any last questions?